Good
Good evening,
hell.
everyone. Welcome to the History Sidebar. It's nice to see so many of you this evening. Tonight we welcome back Gary Gilbert, a returning speaker who's going to speak to us about exoplanets and search for life. On then, thank you very much, Gary, for coming to speak to us this evening, and over to you.
My pleasure. Thank you, everybody. Okay, so what I'm going to talk about tonight is exoplanets and pretty much very brief recap to some extent of what I talked about last time, with a lot more information about what they've done since and what the plans are doing in the future. So I thought I'd quickly recap on the first one ever discovered, strangely around the pulsar. We never thought we'd discover any planets around pulsars because they're usually from dead stars, from supernova explosions, and we thought the forces would fling a lot of planets out. But they were three pulsars about 1,200 light years away, very distant, some of the most distant planets we've ever discovered. And they were the first, and Drager, as it says there, is only moon-sized. So that's one of the smallest ever exoplanets we've discovered, and it was one of the first. So that was just looking at the timings of a pulsar. I concentrated on a couple of stars last time, Alpha Centauri being one of them. The C1 there is a direct image with one of our big ground-based telescopes on Earth. And we think that's one of the planets around Alpha Centauri, which is the main bright star in the southern hemisphere. But it's a possibility they're still investigating it. It might just be a large dust cloud in orbit around. Now, Proxima Centauri is a star that's in orbit around Alpha Centauri. That's a double star system, and this one has two planets. Basically, Proxima Centauri B and Proxima Centauri C are the planets. There's nothing particularly special about these, but one of them, the red one, obviously goes in and out of the life zone, the Goldilocks zone, which I'll describe a bit later on anyway. So when we're looking at these, we'll have a lot of stars doing what they do. The little green bit in the middle is the Goldilocks zone, where we'd like the planet to be so that you have water on the planet. So you can see Proxima Centauri C, generally they think is outside it, but Proxima Centauri D, which was a proposed planet, which they haven't totally confirmed yet, would be just on the edge of that zone. But for anybody who remembers my last talk, most stars that I'm talking about like that are like that star there all day long, very active, very small, quite dim, not very hot, and the star has planets going around it in terms of days. And that would be in the Goldilocks zone. So when you're that close to a star, you are target practice for plasma streams and things. So not great ideas for life, as I said last time. Another one of my favorite ones, Barnard star. In 40,000 years, it'll be the closest star to us. This star, roughly every 10 years, moves roughly the distance of the moon in the sky. But you'd need a telescope to see it because it's very dim. One of the closest, and you need a modest telescope to see it. So it's not very bright, and that tells you how not bright these are. Now, these are all basically confirmed planets around this, and I'll go into more detail about how we know about these particular planets a bit later on when I look at a bit of instrumentation that we've been using over the last number of years. But again, one of them is roughly, I believe, in the Goldilocks zone yet again. But again, this is another target practice star, very big. Yeah, if there's life on there, God, it must have shields and everything. It must be like Star Trek. It must be brilliant. My favorite star of all is Tau Ceti because it's the nearest what we call sun-like star. Okay, so it's a bit like our sun. It's about 55% the brightness of our sun. So it's kind of a mini version of our sun. And our sun is classed as a yellow dwarf. So we are starting to get a bit smaller again. So again, loads of proposed planets around this one. But this is the funny one. I wanted to include this slide because most of these, we're not even sure if they're there yet because we haven't directly imaged them. And the instrumentation that was used to find these, some of the people followed up the readings a year later and went, you might be looking at something else on the star. And I'll explain maybe a bit more about that later. So the science of finding planets around these things is not as clear cut as you might think. But most of what we find, in some cases, are definite. We'll see some fantastic evidence a little bit later. A quick note of the Goldilocks zone. Our sun at the top. There's our zone. We're in the edge of it. Mars is in the edge of it. Okay. I'll remind you, our sun is getting slightly brighter, slightly warmer over the next several billion years. And we'll be outside that zone, and Mars will be in the middle of it. Might be a good place to go. I'm not a fan of Elon Musk, but it might be a good place to go. So the idea is, now we can compare it with Tau Ceti. It's nearly as bright as our sun, but look how much closer in that Goldilocks zone is. So this is why we like to look at stars a bit similar to our sun. And if they're really small, like Barnard's star, they're terrible candidates for life. Great candidates for planets, but terrible for life. So you can see here, it's still far enough away from the star that it's not necessarily doing target practice. And the good thing we can do with stars these days is we can look at them and go, how active do we think they are? And we look at it with a telescope and we can basically go, it's a normal star, not doing too much. It's a Barnard's type star, red dwarf, going crackers all day long. And then there's bigger stars again, and they're a different story altogether. I might mention them later if I can recall it. So our sun in the middle is a G-type dwarf. An A star is a super bright star, so a bit like Rigel in Orion, bottom right-hand corner, if I remember rightly, opposite Betelgeuse, which is a super red giant. So that's an A star. That will only live for 200 million years. Not a lot of time to get a colony of ants going, so it's not a great prospect for the bigger stars. The M stars, which are getting towards the red dwarfs, you can see a bit more like Tau Ceti. They're still prospects. Okay, it's the stars a bit below M, which are what we call these little red dwarfs, and they're terrible prospects, and they're 95% of all the stars in our galaxy. So 95% of all the stars in our galaxy play target practice with their planets. So straight away, life isn't set up to be proliferate. So what have we been doing? Well, I mentioned this one last time. I'm not going to spend too long on the Kepler mission, but something I didn't show you particularly last time is, not that you'll see it all, but this bit here with a little cross, that's Cygnus the Swan. Okay, so you know roughly where that is in the night sky, just a cross of stars. It looks a bit like a swan. One of the few constellations that looks like what we call it. And just off the right arm was where that thing looked for a couple of years. That's all it did, was stay on the same spot for several years, looking nowhere except there, looking at the brightness of every star in that image, or the non-bright ones. I'll go into that in a minute. All the standard low dim stars. Okay. So it studied that, and basically at the end of its study, it came up with 2,500, well, 2,772 at least, exoplanets, all on its own, just from that one patch of sky. Okay. Now, this is one of the best probes we've ever sent up. The job we sent it up to do, it did it too well. Okay, it was amazing. And it can't do bright stars because they flood the sensor, and you don't get a good measurement of the brightness, the magnitude of the star. So that was never designed to do that. So any stars you see in that image were ignored. They're too bright. It's all the ones in the background that are a little bit dimmer, and the sensor works on and ends up doing what it did. Now, it was so successful, they extended its mission. It was only meant to be on for about 2 or 3 years. I think it lasted 9 years already. It did the Naught mission there, and now it's done 19 missions. Okay, it didn't stay on them as long, so it looked on them for a little while. And what this allowed them to do is find relatively short period planets, because it is looking at these dim stars, looking at those planets, which are usually close by. The longer you look at a star, the longer you can find a planet that's further away. If you look at the sun from a long distance away and try to watch the Earth eclipsing the sun, you have to watch it do it for at least 2 years. You have to have 2 pieces of data because one could just be a fluctuation. Really, you need at least 3 pieces of data. So you've got to look at our sun for 3 years to see the Earth. So that's kind of the next missions. Carry on. That's kind of.
I'm not here.
Nearly invisible. So yeah, basically, he's now switched off. You think he's doing well, this fella. Well,
Click on halfway on your screen.
if I can get my mouse to appear, there we go. There we go. So, a very quick recap on the first few. The Hubble, the one you won't know probably, the Spitzer, the one I didn't even know, the Carrot, and then Kepler. So there were a number of missions before Kepler. It was designed to do exactly what it was designed to do, find exoplanets, nothing else. It wasn't designed to take beautiful pictures of anything. So the idea is the Carrot was a good little mission. That started us off with a few exoplanets before Kepler did. Spitzer was an infrared instrument, and when Carrot found some and Kepler found some, the Spitzer could look at those systems and analyze them in a different way. So not just looking at, is there an exoplanet? It's what can I tell you about the exoplanet? We'll go into a bit more detail on that a little bit later. So basically, Hubble and Spitzer basically did their job. The Spitzer stopped running in 2020. So, the Hubble went up in 1990 and is still going. That still is very useful in what we do. The Carrot, it stands for convection radiation. I'm reading French now, a transit planétaire. Not my favorite language. So the idea is it's just looking at mostly transits, but it's also looking at rotation and convection, believe it or not. It's trying to look at the convection of the planet, which was the first one to try and do it. And it wasn't too bad. So the idea is the next missions, the one that's still up there now, is called TESS. And I like this one, Transiting Exoplanet Survey Satellite. Says what it says on the box. So it's the only job, again, it's like Kepler Mark II. Basically, it was designed to do slightly different stars, though. It could do the brighter stars, and then we've extended the mission. So this one's looking at even more stars. And it's basically starting to produce its own data. Because if you look at any catalogues of exoplanets now, most of them were found by Kepler, because they're still trying to go through all that data. And some of them were found by TESS. And a few were found, as you'll see in a few minutes, from other sources that you might not have thought. My favorite one, because it's one that is basically going to do what I'm now more interested in exoplanets. It's called the Characterizing Exoplanet Satellite. Basically means we want to know what's there, not just that there is a planet. Does it have an atmosphere? Maybe what temperature is it? What mass is it? We're trying now to find out far more complex information about exoplanets that are anything from 10 to 100, 200 light years away. Okay, remember the nearest star is over 4 light years away, and there are only maybe 50 stars up to about 20 light years. So there's not an awful lot of stars close by. So we're not concentrating on them all. So its main science goal is to study the structure of an exoplanet. So it's moved on from Kepler. It's not just looking for, it's not doing any transit stuff. It now looks at what Kepler found. It says, what can I tell you about that planet? So we've moved on. What we need to mention is just a little bit of science, and there's a couple of elements of science I've thrown in for the lab. Most telescopes we send up there now kind of do that. The telescope I have in my backyard is what we call a spherical mirror. That's hyperbolic, because that does a far better focusing mechanism for any light that's coming in parallel, and you get a far better image right to the edge of the field. When I look through my telescopes, the center of the field is nice and good. If I look out to the edge of my field, I see what I call comets, okay? Because my system can't focus the edge of the field as well as the center. This thing focuses from edge to edge. So Hubble was designed like that. All the biggest telescopes in the world are now designed with that style. Far more expensive to cut your mirror in a hyperbolic shape. Not easy. When people were maybe 9 or 10 years ago, we're talking 70 years ago, they used to grind their own mirrors at home. Okay, with pitch black and a mirror blank. So the idea is they're doing that, and they're going to make a spherical mirror because it's the only thing you can easily do at home. Question? Okay, the biggest hyperbolic individual mirror, I believe, on Earth might be 10.1 meters. Okay, we don't make many individual mirrors bigger than that now for reasons you might see in a little while. That's just, wow, it's bigger than this room. And you stick it on a truck and you've got to take it up a mountain. Wow, let's just not go there. That just sounds like something I don't want to do for 2 weeks, is how long it would take you to crawl it up there. So they make more like this now because the best instruments need the best optics. It's as simple as that. My one at home, I only need to look in the middle, so I'm not worried. By the way, anyone wants to ask a question, please just break in. The web, well, we've heard so much about this. I just thought I'd mention it very briefly. That's kind of what the web does. I'll go into more detail in that in a little while. So the web can look at exoplanets. It isn't one of its primary missions, but because it was designed before we'd really found any exoplanets. It wasn't designed with exoplanets in mind. It was designed with deep space, edge of the universe kind of science. So the fact that we use it for this is amazing, and it can do detailed examination of an exoplanet, probably better than any telescope on Earth, just about. Again, it is very infrared. Okay, the next slide helps us with that. What we see there to us would be completely black, motionless, even if we were standing next to the object, because there's a filter in front of each of them, and we falsified the color so we can see them. They're all invisible light. So they, a bit like the Hubble, but even more so James W. Webb, it does not take photographs of things we can see. When it takes a photograph, and there's some brilliant looking photos, it's all invisible to us. You might as well have a bee looking at it with some infrared ultraviolet vision going on. And that would seem more like James Webb than we do. So we falsify them so we can see information and they look pretty for us, non-astronomers especially. We try to make the science look pretty. That way people don't moan when we're given 5 billion quid to build something that big. Yeah, so we do try our best. So they're measures of frequencies, and they can tell us something about the planet itself, the temperature, the albedo, which I'll mention again in a little while. So what the main part of what they've been doing around the world is building instruments, which we attach to some of our ground-based telescopes. So this old telescope here, I'm not even sure which one that is off the top of my head, but they made an instrument called HARPS, and it's high accuracy radial velocity planet searcher. I think they make up the word and then make it fit. Otherwise, these things never sound that good. But basically, this thing can be attached to a telescope, and you can look at a planet that's 100 light years away, and you can basically, or you can look at a star, and you can tell if that star is coming towards you or away from you at as little as 1 meter per second. I think, wow, most of the people I know can't even do that on Earth. Okay, and some of them are scientists. So that's kind of precision of looking a long way away and seeing that kind of data. And I'll go into a little bit more detail about kind of how we do that in a short while. Another one, high res, kind of says what it says on the box, high res, okay, high resolution. And those in high dispersion, a shell spectrograph. I know a shell is a special type of spectrograph, don't know the detail of it, but that's one of the telescopes, which I thought had a label with it, which I don't. I think that one is the Gemini telescope, which is 2 8-meter mirrors, 2 separate telescopes, but they can link together. So the idea that we're building instruments now which can be attached to these telescopes, and they do a little bit of a job. This one I like because this was one of the early ones, used the Maroon X on the Gemini telescope. So there's the Gemini. It's 2 telescopes and 2 8.1 meter ones. I was nearly right. And it's called Maroon X. They should have called it Maroon 5, but I think they missed one there. So the idea is, this is one of the ones used recently to prove that data I showed you earlier. It basically said, it looked at Barnard Star, and what Barnard Star was doing, as these planets go round every sort of 5 days, 10 days, 15 days, they pull on the star, and the star's either coming towards us, or the star's either going away from us. And then if you do a bit of mathematics on the data, Gaussian elimination, all that stuff, it tells you you've got a planet there. Because you have a frequency of things happening. Every 5 days it gets pulled towards you. Every 5 days it gets pushed away from you to 10-day orbit kind of thing. So the idea is these devices can measure something in the spectrum, which we'll go into shortly. I do want to mention, most of these were discovered by Kepler because the name itself is on there. But one of them, the other ones are called Gliese, because that's a star system which is very close to us. Probably about 10 light years away. And we've been looking at a lot of the closest stars to us because we can measure them more accurately and we can measure them more easily with any instrument on Earth. So the idea is we started discovering these, and these are what we consider habitable. Yeah. If they're around these little red dwarfs I was talking about earlier, the idea of them being habitable, I'll tell you something, if there are aliens on there and they've survived that, and they come towards us, we wouldn't see them coming. They've got some special skills. They make the commandos look like big beasts that can't hide behind a big building. So it's just basically from the Kepler mission, we found a lot of habitable planets. There's a lot out there. I will move that on. Yeah, don't want to do all the Gliese stuff. So in 2010, one of the biggest observatories, the Keck Observatory, proposed 2 additional planets, 581F, 581G. I wanted to mention this one because they're on there somewhere, 581G top middle. Astronomers half the time are making up the experiments. And what they do is they create what's called a model. They get the results from their experiment, they compare it to the model, and they say, do we get some statistical agreement? They often get it wrong. Is a simple answer, because 6 months, a year later, somebody else does another set of data with another instrument, doesn't get the same results. And this is the good thing about science in general. When we say we found the planet, we found the planet. When we say there's a proposed planet, we're still looking, we're still checking, because we're not totally sure, because maths is just number work, and that doesn't always give us the truth. But most of what we're finding at the moment, they will probably all be very, very likely planets around there, likely stars. And we've been moving on through them for a long time. So again, these are all in the habitable zone. So these are all in that little green zone around its star. I know some of these are around red dwarfs, but some of them, I'm not sure of any of them particularly. I know the Tau Ceti is normal and the Earth's normal. I don't think any of them stars at all. HD 4037, that one might be a normal star as well. So the idea that the stars we're looking at with a telescope, most of them are really horrible places to live if you're in the habitable zone. You might as well be dark practice for somebody who's really good, so they don't tend to miss. So what are we basically doing in the future? Well, quite simple. The Plato mission, it's like coming back on, planetary transits and oscillations of stars. Now, there's a nice little title within the description. Basically, it's planned to launch next year. Knowing the launch of everything else, it'll be in about 4 years. So it never goes on time. And what we're looking at there is, it's not really designed to see transits. It's actually looking at the star. And it'll see an oscillation in the star. So it's a bit, again, this method of looking at the star coming towards us and away from us. But it's doing more than that. It's actually trying to characterize the star as well. Because if we point something like this at our sun from a distance, our sun, if you've ever seen it, is like a great big lava lamp. It's got big projections coming up to the surface, hitting the surface, and then falling back down again. that in itself causes oscillations on the sun. You can measure them. So this 1 meter per second accuracy thing sometimes could easily be seen as something that we're just measuring on the surface of the star. So that's why we're looking for these things that happen periodically. But sometimes periodically, stars do that trick as well. Because our sun has a 9-year periodicity that does an awful lot of that. So Plato, yeah, studying, yeah, extra slide there. I'll put more information on, that's what it was. Again, it is searching for transits, but it's concentrating on normal stars. So it's now looking at the Tau Cetus and the Epsilon Eridanes and a few other stars that are a bit like our sun, a bit smaller, a bit bigger is fine, a bit cooler, a bit hotter is fine. But when you go down to these little red dwarfs or these A-type stars I mentioned earlier, we don't really want to look at them. I know we've got enough data on them, that's cool. Let's go and look for the stuff where we might find some green little alien living and, you know, communicate with them one day, tell them exactly where we are. So the idea is Plato will be one of the first missions to actually start looking specifically at certain stars. And what these probes often do now is they have, well, we call it a multiplex system, where they have a load of fiber optics pointing at certain spots in the sky. Because it'll look at a certain place in the sky and pick those stars out through the fiber optic. So it's not looking at the other stars. It's not getting all its information. The less information it has to send to us, the quicker it can send it because it's up in space. So Plato and most future missions tend to be looking at a way of looking at individual stars, okay, or groups of individual stars that it goes up to analyze because they set up the fiber optics in a specific pattern, which they can obviously move with the commands of the electrics to the spacecraft. One of my favorites, Roman. It's basically going to be, it's one of my favorites because it's not just about exoplanets. It's a cosmology probe, but they're going to use it for exoplanets as well. So the idea is a lot of these probes are going up now with a double mission. Okay, we do want to know what the edge of the universe looks like, why it's there, and why we think it's 13.7 billion years old. But I also want to know if there's a planet 5 light years away. It's some nice little green man who wants to come and visit me. So study a complete sample of the Milky Way exoplanets and pioneering direct imaging. So this one's going to work in a different way. Direct imaging is like very special. I'll show you some ground-based telescopes can do it. I'll show you that later. So the idea is this one's now going to take pictures of stars, but it uses what's called a spectroheliograph, which basically puts a little disc in front of the star and tries to look around the star. So it's not looking at the planets right next to the star. Because if I had a planet that was, say, around the star only 30 light years away, and it was in the green zone, it's only half an arc second away from that star in the sky. And to explain what that is, that's better than you could ever see with a telescope on the ground from anywhere on Earth. Barring one thing I'll describe later. My telescope, when I take pictures, if I'm having a good picture and take a short exposure, it's about a 2-second blurring of the star. Okay, so these things are going to look really close to the star because they're out of space, there's no atmosphere, and they can look for all the really close planets, but they can look for the further out ones. And we'll see what they're doing with them a little bit later as well. The Nancy Grace Roman telescope, and it's due to be launched in 2027. So that's not too far away, and I hope they're on time for that. What determines habitability of Earth-like worlds? Basically, gravitational micro-lensing is a little task they're going to use, and that's a weird one. It's when an object passes in front of a star. Micro-lensing is when that planet, for example, actually amplifies the light of the star towards you. It's a very strange effect. It takes me a lot to understand it. But because it's right in front of the star, like a transit, it can also magnify the light. I always like to go, how do you magnify light that you've just lost and then detect that you've lost? But I'm still working that one out. So they all use a coronagraph and they're going to stick them in the way of the star and look at them. Aerial, performing at chemical sensors. Now, this is where it really gets interesting. It's nice to know there's a lump of rock around that star, or a big gas ball, or an ice ball. Don't see many of them, actually. Not as many as you think. This is going to tell us what's on the surface. So it'll look at them, and it'll use the technique I'll show you a little bit later. It's just going to say, do we have any chemicals on that planet that are interesting to us? And the idea is that quite a few of them will have and should have, because if we look at all our planets, there's only one without an atmosphere, Mercury. Venus has got the most acidic atmosphere in the entire solar system. Jupiter's got the deepest atmosphere in the solar system. And then the ice planets, well, they've got a very deep atmosphere. I was at a lecture the other day and I was told on Neptune, it rains diamonds because the surface is basically a sea of carbon instead of a sea of water. There you go. Some of the weather stuff they're conjuring up now is phenomenal. So they're doing their studies. So Ariel will do an awful lot of that, and it will just start telling us the kind of stuff we really want to know. I just thought to throw that slide in, a little science. Those people who know why I'm throwing that in instead of just, okay, here's the science bit. The greatest scientist who ever lived, Isaac Newton, basically discovered the spectrum in 1665. Herschel, 135 years later, or whatever it was, find a way of help. Discovers infrared. Took them 130 odd years to find that infrared is beyond the spectrum. Wow, what were they waiting for? Which is, I'm surprised that nobody had looked a little bit beyond the spectrum somehow. And these were good scientists. I mean, Newton was brilliant. I'm surprised he didn't find it, but Herschel was a bit of a scientist, but most of us, if any know anything, he was a massive observer. He was one of the greatest observers of the sky in the early telescope age, basically. And it comes down to this. Fraunhofer lines. They really should be called Wollaston lines or Wollaston lines, because that's the guy who first kind of discovered them, where he just said, oh, there's some black lines on the spectrum. That's where he stopped. Why would you do that as a scientist? But it happens. And then a very famous man now, because I know him as Fraunhofer lines, he came along and said, there's thousands of these lines on the sun's spectrum. And just to give you a clue, that's how we discovered helium. It's exactly how we discovered helium, because there's a couple of lines on there when they took away all the lines they knew from all the chemicals that they knew at that time. And they said, there's these couple of really bold lines. What are they doing there? And they said, this must be a new element. And because it was from the sun, they called it helium, helios. So the idea is that's why we discovered helium. Okay. And every one of them lines, and multiple lines quite often, represent a specific element and more. Okay. So the idea is this is basically the lifeblood of any astronomer alive today who's doing any kind of gas analysis work, shall we call it, or even just deep space looking at things. They're basically looking at versions of this all day, the data for it, and saying, what's there that shouldn't be there? Where is it? And what do I determine from that? So the spectrum determines nearly everything. It's the most powerful tool we've got. And I don't know, this little video will work. Probably hasn't, because it didn't work on my version earlier today. When our planet goes around there, these lines will shift like that. They'll do a little Mexican wave left and right permanently. Okay, and that's what we call radial velocity, because these lines exist there on a stationary object. If you move the object towards you or away from you, those lines move left or right, end of story. That's what you know as redshift. Most people have heard of it, or Doppler shift even more so. It's basically related, it's the same thing. So the idea is all of those early instruments I talked about, the Maroon 5, sorry, the Maroon 10, and the high res and the Andes, they're doing that trick all day long. They're looking at this little shift in the spectrum and going, how little a shift can I detect, and can I detect things that happen every day, every other day, once a week, and attach it to a planet that's in a regular orbit. So this is pretty much the lifeblood of what they are doing. Just slide on there for that. This is kind of what we do with the spectrum. We've already kind of seen that in the previous one I showed you. That is a spectrum of a sun passing its light through a cloud where you're in line with the cloud. So we put a great big cloud of helium in the way of the sun, just helium, nothing else, and you could observe that the only lines you would see on that spectrum would be helium. Okay, you do see faint other lines because the surface of the sun does have some kind of chemicals on it, but ignoring that. And then the other one that we see a lot, we use it for general astronomy, is the emission spectrum. So the sun shines its light over there at a cloud of something, or a sun, and that light then bounces off that and comes to us. And that's this kind of spectrum where most of the spectrum disappears, and all you see are the little coloured lines now. That's called an emission spectrum, where instead of lines, you get little bands of colour. Okay, so it's the opposite effect. It's like a negative photo. Okay, so we're using that to determine most of the chemicals in the universe anywhere we look. That is pretty much the fingerprint system for every star, every cloud of gas that we see in the universe. So it's very powerful. It tells us what we've got. Remember what I did on that one now? Oh yes, transmission spectroscopy. So the idea now, look at that planet. It's just about to eclipse in front of that star. And we're trying to draw something resembling a little atmosphere around it. Okay? We know the spectrum of the star before it eclipses. We see it, we measure it, we see all them lines, we know what we expect to see. When that passes in front of it, we get some extra lines, or we get some bolder lines. And what that tells us is if that thing's got an atmosphere, and if it's partially opaque. Okay? Can't be fully opaque. If it doesn't come through at all, we don't really see it, or we don't see it in the way that we might expect. But what you're now noticing is that instead of just elements, we're now seeing compounds. Compounds have different lines than elements. So if I want to look for water, it has a lovely big thick line in the red part of the spectrum. That one's something we need to look for. And then H2O, again, another thin line. CO, don't want much of that, kills you. CO2 doesn't do you much good either. So the idea is we can see the most influential gases. If it's a really thick line, there's lots of it. If it's a very faint line, there might be a bit of it. So we can even attempt to quantize how much in a little way. Not too much, but definitely in a little way. And that's not the only way we can do it. So we were looking at that one there with the sort of purple circle around it. What happens when, top left, the planet's coming from behind the star? Okay, so you're looking over the shoulder of the star at the planet, and that planet will add a bit of light to the brightness of the star. And when it's in front, it takes it away. When it's behind it, it should increase the light a little bit. For those who don't know it, albedo is just saying how reflective is something. Is it a mirror or is it matte paint? Okay, how reflective is something? So albedo can be measured because it would come in and out of that eclipse plane. And now what we do is we follow these planets all the way around their stars. We look at it when it's in front of the star, behind the star, and we can say phase curves. We can monitor that planet all the way around. We can actually start to see now whether there's a change in the planet's albedo, which we now attribute to change in weather. Because really, there are some planets that would change albedo. Anyone who saw Pluto the other year from the New Horizons, I think it's a false colour image again, so that just winds me up, so I don't know. It had a big red sort of land mass and a big white land mass, and imagine that station yet, and that spins out. So it can also indicate land. Okay, changing the, imagine you've got crops growing over here and the desert over here, very different albedos. Okay, so as the planet spins around, we can start to detect so many differences on that planet's surface. And we combine it with the spectroscope and say, we're detecting oxygen, we're detecting nitrogen. Then we're going to go, that's an atmosphere. Okay, and it's probably got funny clouds of ammonia raining down on people, not giving them a very good day. Okay, so the idea is we are doing so much science with just now following planets, which is why we don't need to find any more planets. We don't send up many more transiting satellites now. We send up satellites that physically look at the planets. We want to know more about them now. The VLT 8.2 meter, VLT, very large telescope. We try and keep it simple. And when I say very large, it's not actually that large. It's only 8.2 meters, which barely makes the top 10. So this is one of the ground-based telescopes that does a lot of work now. And the reason why it can, I'll go into detail in just a few seconds, but basically it's got these 4 8.2 meter mirrors, you can see the big things, but it's also got like a small bunch of 1.8 meter telescopes. I'd love to own one of them, thank you. That would do me. Go and retire there for the rest of my life. So we're doing stuff with the VLT. One of the nice ones it discovered was WASP 121b, called Tylos, 900 light years away. So we're not exactly working next door. And it's got an ultra hot Jupiter. So that means it's pretty close to its star. And some of these things are, everyone knows Jupiter's our biggest star. We call them that for a reason. They're at least as big as Jupiter. And some of the ones we're finding are 10 times bigger than Jupiter, which nearly makes them a star in their own right. So we're starting to find an awful lot. This particular planet has a massive jet stream on it, they believe, because they've been monitoring the planet with that phase technique. And they can also do radial velocity measurements on the planet. Okay, if you do it on the edge of the planet, potentially, you can see either the planet's spinning so supremely fast, or there is something going on in the clouds, and it's going at hundreds of miles an hour. The largest one I think we've seen is on Neptune, 1,300 kilometers per hour winds. Okay, some weird stuff just in our local system, and ours is a boring system by all accounts. Well, we're in it for a start. So basically, that's a ground-based telescope. Now, how are they doing it? Well, first of all, where they are, Chile, for example, they're up on the Atacama Desert. They're roughly 15,000 feet in the air just for the flat plains. And then you're going up to about 20-odd thousand feet for the mountains that are sitting on top of the vast plains. So the Atacama Desert is the highest desert in the world, I think. And we stick a lot of our telescopes on top of that because anyone who knows anything about a desert, try. We don't want moisture above our telescopes. Bad for viewing. So we don't do it. It's basically this. I remember this in the days of Patrick Moore, because I remember more or less him doing this display a long time ago. Those 4 beams of light actually exist. This is not a cartoon. I've actually seen one down in Herstmannshow. It's a little satellite tracking telescope, and I've seen the green beam go up into the sky. And what that beam does is it goes up and they measure what comes back. And that allows them to say, what is the air in that direction doing? How is it varying? How is the pressure? What way is it going? It tells you everything. It's amazing. And what they do, and this is the bit that I find amazing. So on the top left of that circle over there, I don't think this works on this TV. Top left circle, there's your terrible image coming from a star. See that wavy stuff? That's because it's gone through the atmosphere. Then it hits that mirror. Now look at what comes back. Because what have we done? We've shaped the mirror. The mirror is not just a simple convex or hyperbolic mirror. It probably is hyperbolic to start with. You've got little actuators on the bottom, like little pressure things, and it pushes the mirror thousands of times a second. And it actually corrects for what the laser is feeding back to say, let's tart our image up a bit because what we're seeing without this is absolute rubbish. Okay, and it literally is rubbish, because I can show you there. On the left is what you see when it's switched off. On the right is what you see when it's switched on. That's air-based. So that's kind of what my telescope would look like. It was taking a picture of that spot, because mine never gets better than that. And then this is what it looks like there. Look at the detail you can see inside that same square. That is just a smudge of nothingness. And now I've got about 20 stars discernible.
No, is correct for that with software?
No, because the image has already come through and it's been obliterated. It doesn't know what it expects to see. If you had software that knew what it expected to see, you probably could do something like that on smaller telescopes to some degree. That might work as a cheap solution for smaller scopes. When I say smaller, 5 meters, yeah, rather than these 8 and 10 meter jobs. So this allows them to do an awful lot of exoplanet work now. Because if you're looking at an exoplanet around that blob, you don't even know what star you're looking at, crying out loud. So here, we're looking at, oh, we can see individual stars, we can look at the star, we can look at if there's something around them. Let's see if this one works. Oh, good, it has, thank you. Okay, bottom left is obviously a calendar. I can't remember where it starts, 2009, 2016. So it's a 7-year video of a star. So they take every few months a picture and they tart it up a lot. And now I've looked at it enough times to say I can see at least 4 planets. Possibility of a few other glitches that might be planets, but it's hard to say. But these planets, the good thing about this is these are not the planets right next to the star anymore, because that circle in the middle is where the star used to be. So they've taken the star away where the coronagraph allows us to see the very faint things around it. Otherwise, the star just blows your camera to bits and you see nothing. Okay, you literally all you see is the star, nothing else will appear. So they've been doing that now for quite a few years, taking actual pictures of solar systems in long period orbits. Because a couple of these planets look like they're taking 100 years to go round or more. That's some of the longest I've ever seen in all of the exoplanets. Most of them are in days. I like this one. Takes 9 years to even go part of the way around. That's more like real planets. So the idea, if we want to look around stars like our sun, we want the planets to go round in about a year. A bit like us, maybe up to 1.5 years, a bit like Mars, because that was in the edge. And it depends a bit less if it's a smaller star, and a bit less if it's a bigger star, and a bit more if it's a smaller star, or the other way around. I'll get it right in a minute. So that, I love that video. I often sit there looking at that on my screensaver rather than doing work at work. Okay, makes me realise I ain't that important. So direct images, again, we can take lots of them. These are false coloured most of the time, sort of infrared stuff. And we're starting to see bands and individual blobs. But the problem with an individual image like that is it could just be a cloud. If you could imagine a real dense group of asteroids around our sun, it would appear like a cloud. So it's hard to say. So we do follow on all of these kind of things. Yeah, I don't need to tell you what stars they come from. It's not that important. Now here's some of the telescopes. I don't care how fancy they look. I'm only interested in the mirror. Because the mirror is the business end of a telescope. So straight away, hasn't been quite built yet, but they're about halfway through. The big green one here. ELT. Extremely large telescope. We do keep it simple. We do, honest. And so many of them are labeled like that. I like one of my favorites is the large binocular telescope, because I think that's 2 8-meter mirrors next to each other, working at the same time on the same object all the time. It's a binocular telescope, but it looks at the same object. What that does is if you space out mirrors, you get what's called an interferometric effect, which basically means that mirror acts like the spacing between them. Okay, so if my mirrors are 20 meters apart and they're 5 meters each. They act like approximately one 20-meter mirror. So you can build smaller mirrors with a little bit of separation and use some extremely good timing and fiber optics to combine the signal. And you have a telescope that's pretending to be 20 or 30 meters. But the obvious side effect is it doesn't have the light grasp of a 20 or 30 meter telescope. This thing will see faint things, end of story. It will only resolve, because I think it's 30 meters, the green one, it'll only resolve something to its 30 meter limit. So that's its resolving power, 30 meters. It's also its light grasping power, 30 meters. Whereas these two here might have a resolving power of 30 meters, but their light grasp is 11 and a bit meters. It will be more than the individual mirror, but not just double. I wish it was. And we set up telescopes everywhere. So lots of smaller ones. And when I say smaller ones, these were some of the biggest in the world till we tried to go on to the 30-meter telescope. And then that's the 30-meter one, sorry. The extremely large, I can't even remember how big they're making that. That's got to be at least 40 or 50 meters. I've forgotten how big it is. It hasn't been made yet, so it's not in my psyche yet. Whereas the 30-meter one is in the, I think it's nearly built now. It was planned. It's going on Mauna Kea, another big group of observatories, where when we get permission off all the natural people who live on Mauna Kea, we have to ask for permission to build things on their island, and they usually give us it if we give them lots of money. It kind of works favourably for them. But we have lots of big telescopes, and many of these are doing that laser trick, and they can really look at fine detail throughout anywhere in space. Okay, so what's this one? It's that little star in the bottom left corner. This is K18b. That means it's a Kepler object. It's K2, which means it was on the second mission. It was on that wherever it was looking when it was in Gemini, basically. Very close to Gemini. And what this has done, it's found a super Earth located within the habitable zone. Okay, and that was in 2015. So we're finding, when we say super Earth, it usually means it's not an Earth. Okay, it's an Earth on steroids. It's more like Neptune, but it's kind of weird. I don't know why they call them super Earths, because it doesn't make any sense logically as a scientist to me. So it's the first exoplanet, hydrogen-rich sub-Neptune atmosphere, characterized water vapor, methane. We've looked at it and gone, it's got water, it's got methane. Okay? We don't need oxygen for life. There are so many other ways to do life, so don't worry about that. Carbon dioxide, and here's the nice bit. We didn't detect any ammonia, which sounds odd, but that makes it an ocean world. If we detect water without ammonia, it'll be an ocean world. Chances are it is literally a ball of rock, if you look in the middle, where there may be a small outer shell of solid hydrogen, and then some of the other solid bits might be around it, and then you'll have water as a literal ocean all the way around the planet. This is water world. Okay, we've all seen it. It was a bad film, but we've all seen it. Okay, so we have these descriptions for these things, and we found a great water world there. Aquatic life. I think the dolphins have a far more intelligent life than us. Let's be honest, they have far more fun until we put nets in the ocean because we're stupid. Okay, so you know, animals are different things. Discovered in 2017 by radial velocity with the HARP system that I mentioned earlier, was another planet, and it's another Neptune-like planet. So it's similar to 18b. So that one's got two planets going around it. One of them is in the habitable zone. We think it's a water world. Sounds remarkably interesting. I wonder if there's a sort of rocky island growth somewhere, you know, fantastic island or something like that. There's the big thing about this particular planet, and it leads on to another story in just a moment. I'll read the word because it's chemical. I'm not a chemist. Correct me in a minute. A dimethyl sulfide. Okay, you're a chemist, not a biologist, so you won't know the significance. It's meant to be an indicator of life. dimethyl sulfide on this planet only occurs through living things, as far as is known. And that's what I'll say, because I don't agree with them. What their current consensus is, when we're starting to find some of these really specialized chemicals that we think are only attributable to life, it's not as obvious as we think, because there are so many atmospheric conditions out there, so many weird planets, that these things might be able to create their own unusual set of chemicals in an unusual way. Different temperatures, different pressures, because these planets have pressures at the middle of them where there's still liquid from water or ammonia or methane. God, what the hell is going on in them kind of pressures? We barely get to that kind of science on Earth. So we're still looking at it. And it is a very interesting area. I'm not a genius on it, but I've seen a few programs on it. So I know just enough to be dangerous. I mentioned the statistics now, because this is what makes me laugh about this one. They did it to a 3 sigma level. So they had their model, they collected some data, and they put the data to their model, and it agreed within a 3 sigma level. That just is a statistical word for, it's not that much. Literally is what it means, 3 sigma in the science world. You start with 5 sigma, which tends to, I'm trying to remember the number, about 1 in 10,000 would produce that same result by accident. Okay, 3 sigma is about 1%. So that's not, 1 in 100 experiments would accidentally produce the same result. We don't like 3 sigma. And going back to something like the LHC and the Higgs boson, we did that to 10 sigma. So when we found that one, we said, yeah, we're not arguing about this result, okay? Unless our entire model is a complete load of balderdash, this is the Higgs particle. So they do things like that, and they do an awful lot of looking through. Just wanted to make a comment a few years ago now. It was, I can remember, phosphine. Phosphine, another chemical we think is only attributable to living things. But here's the deal. We couldn't repeat the experiment. It reminds me of cold fusion. Who remembers that one? We all thought we were going to have free power. And then somebody else tries to repeat the guy's results. Nobody can get in there, and we'll start laughing at him, and deservedly so. I don't blame the scientists for this. I blame the press. The scientists will have said, oh, phosphine is a life element. It's fair enough. That's what scientists should say. And then the press person should ask more questions. Not just go, oh, we found life. Big press, like, oh, I love the headlines. So Venus, for a good while, a year or so, we thought, what the hell is the explanation of Venus? And we thought there was life on it. And God, anyone who knows anything about Venus, it's 100 times the pressure of the Earth at land level. The surface temperature is 425 degrees C. And you have to be about 7 miles up in the air just to be at a temperature of about 10 or 0 degrees in the upper atmosphere. So the only thing that could live on there is some little microbiomes that seem to have found their way to living in a shell around Venus, where they don't burn to death or freeze to death. Sounds like a really tricky deal. So I was never a fan of that when they found that. I laughed as soon as they said it. Okay, these are the kind of things that appear on my feed, on my machine when I'm at work. I go, yeah, that's a reporter's story. And then, oh no, that's a scientist story, and I'll read that one. There's the important bit, which we can end here. Final thoughts, 22% of sun-like stars have Earth-sized exoplanets in the habitable zone. I will temper that a little bit, because that sounds far too optimistic. Only 6% of stars are anything like our sun. Okay, so you start from 6%, now you're taking 22% of that. Okay, and then take a bit off of the really bright stars, take a bit off of the really dim stars. It does go down, but that relates back to a talk I did a while ago, Drake's equation. The idea is we do start to have probabilities for what's the likelihood of finding a planet that you could stick life on. And it's as simple as that. There are loads of them out there because we have 400 billion suns in our galaxy. and ours is an average galaxy. Okay, the Andromeda is bigger. They reckon there's at least 400 billion stars in that one. So, and in 4 billion years, that has a nice collision with us. That's good fun. We can all watch the fireworks if we've got our head in a jar, like the Simpsons. That'll be fun. So, basically, the story of what have we been doing, what have we done, and what are we doing of exoplanets. Thank you very much.